Thank you. Thank you for being here. Firing on all cylinders, almost. All right, so we'll let a few more people in, and in about a minute, we'll get started. So, sorry for the awkward silence. Okay, now is the time. Good morning again, if I haven't said to you yet. So my name is Frederic Detienne. You were probably expecting Jay Young, to give the presentation today. Unfortunately, Jay had a family issue that he had to attend, and he couldn't make it, so I will be presenting on his behalf today. So for those who already had session with me, I know usually these are very fast-paced sessions, and I will try to adapt to Jay's style, which is more, like cooler, softer. I have way less slides than I usually have. So don't be scared, it's Friday, we'll take it relax. So yeah, thank you again for being here on a Friday. I know, it's been a rough week with all the partying and all the presentations. I mean, I think, like I said earlier, if I had to attend all these sessions, my brain will leak out of my ears. So anyway, thank you for being here. So if you don't know me, my name is Frederic. I'm a distinguished engineer. I work in the TAC, in the CX organization, so called Customer Experience. How many of you have been made aware of that change inside Cisco? So have you heard about the CX department? Okay, only a couple of persons. Thank you. So essentially, the TAC stays as it is. The department, the support department, will stay as it is. But we actually are revamping our entire services organization to try and make sure that whatever we sell in terms of devices, in terms of services, is more in line with what you need versus what we'd like to sell. So I'm really hoping that you're going to see a different experience in terms of support, especially from a sales standpoint. But from a reactive support standpoint, currently there is no planned change. So if you have feedback on that, we'd love to hear it. Of course, customer satisfaction scores and surveys will keep coming. So anyway, so that's a big thing to say that I'm part of this CX department, but I'm from the TAC. And I'm also the happy author of DMVPN and FlexVPN, and I have been working with crypto, IPsec, and all of that since before they even were RFCs. So that's really way, way back. So today we're going to talk about IP security with a strong focus on the negotiation protocol called IKE, Internet Key Exchange. And so at first I'll be presenting how IKE version 1 works. You may have heard about it as ISAC-EMP. And then we'll be looking into IKE version 2 and draw a comparison. So who attended the crypto presentation? Quite a few of you, but not everybody. So I'll try to, at the right moment, insert the concept that we have seen over there. So, we'll see where everything fits really precisely. But as you will see, there is nothing really complex any longer. All right, so IP security. Well, it dates back to 1998. The truth is that it took a while to get there, right? So we had like pre-versions or drafts of this, and it took several years to actually form to what became a little later as IKE version 1 or ISAC-EMP. It's a protocol that's supposed to support multiple strong authentications. So, back then, we had solutions that were completely proprietary. Everything crypto-related was extremely expensive. You had literally to buy military-grade equipment, government-grade equipment. Everything was like, supported one use case, maybe two use cases, and that was about it. And of course, when the software got obsolete, you pretty much had to forklift it and replace it because the hardware wouldn't cope with evolution. So they wanted to create, because I was too young to actually influence at that time, the plan was really to create a protocol that would support multiple authentication methods, support multiple cryptographic algorithms, and something that could evolve over time. All right, and actually it was a success because we went from DES 40 bits to DES 53-bit or 64 bits, no matter how you want to see it, then to triple DES, and then to AES, and all of that quite successfully inside the same protocol, just by changing a few numbers here and there. From an authentication standpoint, pre-shared keys were allowed, so just secret passphrases, but we also finally supported certificate, or we could actually support public key authentication systems with or without certificates. So again, the protocol catered for multiple situations. We wanted the keys to be generated on the fly because we didn't want any of the encryption keys for the data to be permanent. Now, it is possible in IPsec to have permanent key. You can actually have fixed keys in IPsec without IKE negotiation. But IKE should actually cater for generating keys for IPsec on the fly. And why? Because we wanted to have perfect forward secrecy, which means that even if later some of the keys get retrieved, whether it's your private key for authentication or maybe an old configuration of your system were retrieved, there is no way for the attacker to go back in time. They may have recorded the IKE and IPsec packets, and there is no way for the attacker to go back in time and then decrypt, because all these keys are ephemeral. So that's why you have what we call ephemeral key exchanges, and this is catered for by the Diffie-Hellman exchange. All right, and finally, it had to prevent for man-in-the-middle attacks, so ways to prevent that somebody would stand in the middle of the communication, in the middle of the conversation, which is quite obvious when you're physically face-to-face with the participant, but when you're across the internet and all you have are electric signals to be sent, hop by hop, there is no way to know that there is an attacker in the middle. And IKE was designed to prevent all of that. And back then, this really was a revolution. When SSL came about, they pretty much missed all of it. They had something that could encrypt and decrypt packets, to a degree sign it, but it was pretty much a failure in terms of man in the middle. The protocol was severely flawed in many areas, and it took a very long time for SSL to get where it is today in TLS, upcoming version 1.3. And if you go to Wikipedia, I always encourage you to go there, and you see a long list of protocol flaws. It's not to say there was no bug in IKE or IPsec. All right, there were also bugs in SSL as well as in IKE, but I'm talking here about design flaws in the protocol. And this protocol is really, really tight from a security and cryptographic standpoint. So that's something that personally, from a theoretical standpoint, I really like. Now, the drawback of IPsec and IKE is that it's a plethora of small RFCs, well, more or less small RFCs. When I did a rotation in engineering, again, way back, right, in the 2000s, we really had a hard time understanding how IKE worked. And I was one of the first persons to read completely the whole stack of RFCs and IEEE, well, ITUT documents, so for certificate management, IKE, IPsec, ISAK-MP, Oakley protocol, the domain of interpretation, and no kidding, there was a binder, we used to print back then, I had a binder like this of RFCs for IKE, IPsec, and I had another binder that thick with the ITUT documents for certificate management, the X500 specification. So it's really massive, and it really went in the way of adoption. I think that what went in the way of adoption for IKE and IPsec was first this level of complexity, very abstract, very high-level framework, lots of documents to explain to you how things are supposed to work, then documents to explain to you what the payloads should look like, essentially like you had a dictionary, and then you had another document to tell you how to exchange packets with the elements, so the protocol, so to speak, so essentially a grammar, if you wish, and then you had another document to explain to you which numbers you had to fill into the protocol so that it would work. Very difficult to read. I fell asleep so many times. Anyway, so that's what things were. So yeah, that's the landscape. All right, this is what we had. We had the key exchange, so to speak, RFC 2412. We had the architecture documents, RFC 24.8, 24.01, 24.11, and then we had all the description for the hash algorithms and the crypto algorithms and so on. RFC 24.03, 24.10, etc., etc. Then the encapsulation protocols are again in a separate document, 2406 and 2402, all right? And then we had protocol definition, RFC 2407, 2409, the DOI and IKEv2. So this is really like, these are architecture document and to a degree the vocabulary set, the architecture document, vocabulary set, grammar of the protocol, all right? And here, the grammar of the data plane packets, and over there, the algorithm that we could use, all right? And the DOI, what we call the DOI, was really which numbers you had to fit in the various places. So really complex, like I said. Another difficulty in IKE and IPsec, if you compare with SSL, is that IKE and IPsec make a strict distinction between the control plane and the data plane. In SSL, you negotiate a TCP session. And inside the TCP session, you authenticate, negotiate some keys, start encrypting, decrypting, etc. But it only applies to the TCP session that contained the exchange. Whereas in the case of IKE and IPsec, IKE takes care of negotiating keys. So first takes care of authenticating, negotiating keys, etc. And then it passes those keys to another set of protocol which take care of carrying the data. So you could actually have an IPsec IKE implementation inside TCP by just, opening a TCP connection, doing an IKE exchange into it, and then start exchanging the data over the TCP session exactly like SSL does. We could do that, and for some reason, nobody ever did. Instead, we developed a complete new set of standards called SSL and TLS, which were kind of bundled in the session. So in the case of IKE, we have what I would call a control plane. And if you follow the ASR1K, well, IOSXE architecture class this week, all of that happens what you call the RP, the root processor of a system. IKE is a process at the same level as, let's say, BGP is, or EIGRP. it talks to the neighbors. Whereas IPsec sits in the data plane and is responsible for encrypting, decrypting the packets and forwarding them and encapsulating them and sending them to the right remote peer, all right? Pretty much like GRE does. So that's an encapsulation format, all right? So we have a clear distinction, okay? So, and by the way, if you want to make a comparison with, let's say, BGP or EIGRP, you have to think about the control plane, BGP, EIGRP, talking to the neighbors, exchanging routes, and when they're done, they compile these routes into the routing table, we compile that into Ceph, and we push that into the hardware, and the hardware uses this compiled table to actually forward packets. Like BGP never forward packets. BGP prepares routes that the forwarding plane will use, exactly like in IPsec and IKE. Oops. All right, so there are two phases because of this. Well, it's not because of this, but I think it's important to notice that there are clearly two phases. In what we call ISAK-MP or IKE version 1, phase 1, all right, this is used for really the control plane. And in there, we actually establish trust between two peers. So we have a first contact between two peers that need to securely talk to one another. We authenticate each other. We generate session keys and make sure that everything that we say at the control plane level inside, between the two peers, again, control plane, right? So communication strictly intended for IKE itself is completely secure and encrypted. Then IKE proceeds to what we call a phase 2 exchange. So over that secure channel phase 1, we start negotiating keys. And when we will be done with these keys, we will push that into the data plane and instruct the data plane to encrypt packets and sign packets using these keys we have just generated into the control plane. All right, so that's really a two-phase system because there are really two layers in IKE and IPsec. Data plane, control plane. It's a very important distinction. It's essentially, if you look at the OSI model, IPsec would operate at the layer 3 level. You could even possibly argue layer 4, but it's mostly a layer 3 model. Whereas IKE is a layer 7 protocol. It's an application that runs on top of IP. All right? So as a matter of fact, IPsec was initially designed for IPv6, and what we call the ESP header in IPsec is technically an extension, an IPv6 extension header for reference. So there are multiple steps inside the phase 1 establishment, and there are two main ways to establish a phase 1. So there are two main ways for two routers to say, all right, I'm Fred, you're George, and we want to talk to each other, right? There is what we call a main mode exchange, and then there is what we call an aggressive mode exchange. The main mode exchange runs in 6 packets. I think it is it's not only the most secure, but it's also the most didactical. This is the one I'll be focusing on first. Then we have aggressive mode. That is a 3-packet exchange, so it's much faster, but it has some security risks. It opens to a denial of service attack. It's really trivial to understand. The risk is not so bad. I mean, it's not like we have seen so many of these because it's kind of stupid to do a brutal denial of service on IKE. But it's there, and it bothers some people. Little less secure, because it leaks out identities. Yes, and because it's more compact, it's a little more difficult to understand at first glance. So I'll be focusing on phase 1, main mode first. What do we do in main mode? Well, it's going to happen in 3 main phases. So I like to try to break it down. So we have main mode, well, we have IPsec, IKE phase 1, IKE phase 2. IKE phase 1, the two devices start to talk to each other. IKE phase 1 can be done in 2 ways, main mode or aggressive mode. And inside main mode, we're going to split the negotiation into 3 phases. All right, 3 steps. The first step is the routers or the devices start talking to one another, and they start exchanging their capabilities and how they would like to secure the communication. All of that happens in the clear. In the next 2 packets, we will be performing what we call a key exchange. That's where Diffie-Hellman comes in. So if you went to the session, the crypto session, that's where we manage to negotiate keys in the clear. So all of that is in the clear over the internet. And the devices manage to generate keys that they will use later on. And in the last two packets, we start using these keys. So the last two packets of phase one main mode will be encrypted using the keys we have just generated. And here is where we're going to do an authentication phase. So we're going to prove to the other device that we are really who we claim to be. And during that authentication phase, there is a side effect. We will be able to verify that there was no man in the middle, because Diffie-Hellman itself cannot protect you against man in the middle. It can create keys that, if it happens properly, nobody can figure out what these ephemeral keys will be, but it's open to a man in the middle. So in the last two packets, we'll make sure that this man in the middle has not occurred. All right? Pretty much here. Okay. So we will do, after main mode, we will proceed to what we call a quick mode, which will generate keys for IPsec itself. Let's move forward. In main mode, we also exchange certificates. So like I said, like in main mode, we're going to authenticate with each other, right? We're going to, at the end of main mode, we're going to tell to the other party, hey, I'm Fred. The other party will say, hey, I'm George. And I will prove I'm Fred. And the remote party will say, I prove to you I'm George. But how do they prove to each other? Well, we could have a secret, a pre-shared secret, a pre-shared key, like something we have agreed upon in advance. And we're not going to send, blindly that key, even though the channel is encrypted by virtue of Diffie-Hellman. We're not going to change the key. I'm not going to say, hey, George, I'm Fred, and my key is Cisco123. Why? Because if we underwent a man-in-the-middle attack just before at the Diffie-Hellman level, even though I would send that key encrypted, now the attacker has the pre-shared secret. So I would have to reconfigure both my devices. And exchanging keys and distributing them securely is another challenge. It's not covered by IKE itself, but how you set up the credentials, it's another level of configuration distribution. So what we really like to do in this case is have a system where George will send me a challenge, like a random block of data, and say, hey, Fred, prove that you're Fred. And I take this block of data and I encrypt it with this, or I hash it with the secret key, and I send back the hash to him. And George will do the same. It will take the random number he generated and hash with the pre-shared secret. And if he concludes with the shared secret, then he will know that I own the shared secret, and therefore I must be Fred. That's how pre-shared keys would work. But another way of doing it is by exchanging certificates. But now there are some challenges at exchanging certificates, so we'll cover that in a moment. Anyway, this is all the stuff that IKEv1 or IKE does in the first phase, and we're going to illustrate it. So packet number one, which we call MM1, main mode 1. So that's the first packet of phase one main mode exchange, will contain a security association number, and VID means vendor ID payload. And in the essay part, we will have the crypto settings. What crypto settings? I would like to use Diffie-Hellman group 2. I would like to authenticate you using RSA signatures. I would like to generate a channel with you using AES 128 bits. I would like, etc., etc. I would like a hash this. I would like a PRF, a pseudo-random function generator, that, all the cryptographic parameters. And George will respond. The responder, we call the other party the responder. The initiator is the device that starts the negotiation. The responder is the device we want to talk to. Both can initiate. There is no preferred role. In practice, there are preferred roles, especially in the case of remote access, but it's a fully symmetrical protocol. So essentially, George agrees. The responder agrees, says, yep, I like your transform. I could say, oh, I would like 3DES or AES 128. And George will say, no AES 128 today, just 3DES. It's bad, all right, but that could happen. So the initiator could propose a whole set of algorithms to use, and George will have to pick the preferred one in that stack. So essentially, at the end of this, we only are going to use one set of algorithms, and that's one hint to say there is no need to configure everything possible on the router. Like maybe I want to do AES 256, then if not AES 128, then 3DES, then DES, then like fallback, fallback, fallback. Don't bother. Just configure one on each side, and that is sufficient. If you know what you want, that's it. Okay, so once we have agreed on the Diffie-Hellman group, in this vendor ID over here, right? In the SA negotiation over here, then we're going to generate the Diffie-Hellman value. Then again, I'm not going to do it today. You can go back to the crypto session. It was recorded. But this is when we create, we choose a generator and a generator function, and then we perform the Diffie-Hellman exponentiation. And so the initiator sends its Diffie-Hellman value to the responder, and the responder does the same. They compute, and ta-da! They come up with a number that both of them know. So this is in the clear, right? This is all, everybody can wiretap this. Anybody can wiretap this. They come up with a number that nobody else knows. Only them. A very hard problem to reverse. You see all the exchange, you really can't figure out how they made it. All right, unless, again, quantum computers, unless we use outdated security policies or outdated algorithm, which means today, group 5 is the bare minimum, Diffie-Hellman group 5, you really should go to the next levels. Once we have these Diffie-Hellman secrets exchanged, we generate a lot of keying material. So we expand that number, we hash it, we duplicate it, we do a bunch of mathematical operations with it, and out of that we create the keys that we are going to use for our control channel. Now IKE, the two IKE peers, the initiator and the responder, will say, okay, now we have an encrypted channel. There may still be a man in the middle, and I'm not too sure I'm talking to the right person. So now, in using the keys encrypted that we generated here, we encrypt the last two packets, and the initiator will say, I'm Fred, all right, and here is the proof I'm Fred. I'm going to use either my certificates or my pre-shared key to prove to you that I'm Fred. And the remote side will validate that and prove to me that he's George. So use his secret key, his certificate, and so on to prove to me he's George. So far, so good? Yes? Too fast, too slow for Friday? I'm sorry? All good? All right. So now, same thing. I'm going to redo exactly the same thing, except now I'm going to do it in 3 packets instead of 6. So this was, like I said, very didactical. It's secure. It takes 3 round trips. All right, so 6 packet, round trip, round trip, round trip. How much time does it take? If your round trip time is like 50 milliseconds, well, it takes 50, 50, 50, 150 milliseconds have elapsed, plus the processing time if there is any. Processing time is microseconds, all right? So let's not even count that. But that's 150 milliseconds. This is 3 packets only, so maybe 75 milliseconds. But with drawbacks. So what happened here? So first off, it's less didactical. So everything that we did in main mode, like across packet 1, 2, 3, 4, we do it in 1 here. So essentially, the initiator says, oh, I would like to do Diffie-Hellman group 2. I'd like to do AES blah. I want RSA authentication or pre-shared key. And I want this pseudo-random function, da-da-da. And by the way, here is the Diffie-Hellman value, and here is who I am. I'm telling you my identity in the clear, and I'm sending you a Diffie-Hellman value just like that, off the bat. All right? I'm just assuming that, yeah, I'm pretty certain you have this configuration. And so if it's right, the responder will say, and no, notice it's not a red packet, it's not a green packet yet, so it's partly encrypted, but partly in the clear. So it will say, I'm fine with the parameters you sent. I agree with the crypto policy that you want to apply. Here is my identity, and here are my Diffie-Hellman values. And by the way, here is the proof that I'm really George. And that part will be encrypted. The rest has to be in the clear because it contains the Diffie-Hellman material, which still needs to be read so that we can compute the key. So what really happens is that we send the Diffie-Hellman material, so the initiator sends to the responder. The responder generates its Diffie-Hellman material, computes the encryption keys and all of that like he should, and uses that to encrypt the identity and the authentication payload. But he still also needs to send the keying material, well, the Diffie-Hellman value to the initiator so that the initiator can generate the keys, right? Now, from this point, the initiator starts computing, generates the keys, and in a last packet, sends a full identity, including and adding a proof of identity. So this is where the device proves who it is. Okay? So same thing, 3 packets only. Now what are the problems? Well, we expose ourselves to a man in the middle. We could start bombarding the responder, random spoofing, right? Like blind spoofing. We can start bombarding the responder with plenty of initial contact or initial messages. We call the message aggressive mode 1. So the previous exchange had MM1, MM2, MM3. It's main mode 1, main mode 2, main mode 3 packets, and so on. And this is called aggressive mode 1, aggressive mode 2, aggressive mode 3. Some people write it as AG1, AG2, AG3 if you go to the literature. Anyway, but we could start bombarding the responder, with a lot of initial contacts, with lots of, each time with a different keying material, so Diffie-Hellman value, and we can actually very quickly clog after, a couple dozen packets, we can completely clog the responder because it's so busy computing Diffie-Hellman before responding. Okay, so that's the problem with aggressive mode 1. The other problem is that we expose the identity. However, there are still some advantages in using aggressive mode 1. We'll come on to that later. So that's phase 1, all right? Now, we may want some additions on top of that. So who is familiar with EasyVPN or remote access with IKE version 1? Yeah, I see that the knowledge starts fading away. I mean, in the past, everybody would have raised their hands, but that knowledge is fading away because we're going away from it with an eConnect, with SSL, and with IKE version 2. But anyway, there were challenges. Okay, I can authenticate this computer connecting to a head end. How can I authenticate the user that is at the keyboard? All right, what is the proof of identity? Can I give a secret key to everybody? Well, no, I can't. Can I give a certificate to everybody? Well, no, I can't. I really would like them to use my LDAP server or my Active Directory or, whatever, or my Radius server, whatever you have to authenticate users. And that was difficult within the boundaries of the protocol. So we created extensions like what we call XAuth, all right, extended authentication or extensible authentication. And we had what we call mode config as well. Oh, since you're connecting, by the way, here is the IP address you should use inside the tunnel. Here is the DNS server you should start using from now on. Maybe you should apply this policy, etc., etc., etc. Okay, so after that, we can also, inside this phase 1, without extension, I mean with the base RFC, we can start negotiating what we call phase 2, or quick mode, where we will negotiate IPsec essays. Like now we're ready to really generate the keys and the keying material and all the data necessary so that the traffic can be encrypted. Okay, so let me summarize it so far. We have IKE phase 1, responsible for securing the channel and authenticating between 2 devices. So it creates an encrypted channel and a signed channel between 2 devices so that control plane can happen. And there are 2 ways to do it. It's aggressive mode or main mode. And now we're entering phase 2, which is under the cover of that encrypted and authenticated channel, we're going to create a data plane channel. So now we can exchange data, like your database transfer can take place. You can start browsing the internal resources, whatever, or you connect 2 sites, whatever. All right, let's have a look at quick mode. So the first message is what we call a QM1 packet, quick mode 1. That's where it comes from. And it will contain a request. It's a QM1 request that will contain a security association, so a series of transforms. So a security association covers 2 elements. It's the transform set. Essentially, it is the suite of cryptographic algorithm we want to use. I would like to encrypt my data with AES-256. I would like to hash the data using SHA-2 or SHA-1. I would like, etc., etc. All right? Notice that you could decide to have the control plane encrypted with AES-256, and you could decide the data plane to be encrypted with AES-128. Why not? You can do that. And this you have to do with the type of processor you have for each. Sometimes it's one processor for data plane and control plane, and obviously you would like the same security level. Or you could say, well, it's okay, I want to have really top protection for IKE because there are not so many packets. Yes, it's expensive, but I can pay the price for these few packets. But for data plane, I would like a little lighter algorithm, like triple DES instead of AES or vice versa. because it's too expensive for my CPU. So depending on the capabilities of the hardware, you would choose one suite or another for each phase, or 2 times the same is really up to you. Anyway, the other important element is the traffic selectors. What am I going to protect? And this is where you say, I want to protect traffic going from this network to that network. I want to protect a TCP session going from this IP address, this port, to this IP address, that port. I want to protect my GRE traffic between 2 peers. That's what tunnel protection does. Tunnel protection just creates a policy that has traffic selectors saying, protect the GRE traffic going from me to you. All right, it's implicit. You don't have to repeat the policy. In a crypto map, you have to have crypto ACLs, crypto access list, and this is the proposed traffic selectors is technically your crypto access list, if you're familiar with it. Make sense? So who's familiar with DM and Flex? Oh, okay, not many. Who's more ASA for VPN? Okay, so you're familiar more with the crypto map concept. Who doesn't have IPsec and IKE at all deployed? All of you. All of you have it, so, okay, good. All right, so the responder will say, yep, I like your proposed selectors, I like your transform set, now here is some, I all agree with you, we're fine, let's go. And the initiator will say, okay, we're fine, we can start using the keys. Why do we have this? Because in QM1, there is enough data for the responder to start installing the keys into the database. Into the data plane, sorry. All right? And we don't want these keys to be used right away because it will take a few more milliseconds for QM2 to make it there and for the initiator to process that everything is fine and so that it can install the keys in the data plane. So what really happens in practice is that we generate the material, we send to the responder, as soon as it receives, validates and say, yes, I agree, it will start to gain some time, it will start pushing the data into the data plane. Why? Because we need to modify some databases down there, we have to program some TCAMs, program the crypto engine. Again, if you have seen the ASR1K, you know what I'm talking about. Even if it's pure software, it can take sometimes milliseconds to happen. It's a very heavy process. So we start pushing, because we don't want to waste time. And then we send, at the same time, literally, right, while the hardware is busy programming itself, the control plane sends back the QM2, says, yeah, all fine. As soon as the initiator receives that, it starts pushing the keys and all the keying material into the data plane, and when it's ready, it tells the other side, okay, I'm ready, you can start using it. Essentially, this responder is ready to receive from this point onward. The initiator is only ready to receive from this point onward. And this is the point where we tell the responder, okay, now you can switch over and you can start encrypting traffic to me. I will understand. My data plane will be ready to process. Make sense? So that's why we have this. There is another packet which we call QM4, which hardly nobody implements. If you go to the literature, it's for naive implementations that would wait for QM3 to be there. We have what we call the acknowledgement bit set. Anyway, not very important. Okay, so we're all good, aren't we? What else could go wrong? What am I missing so far? Huh? I'm sorry. NAT, yes. And thank you. NAT, that's a big issue. NAT break things. Actually, did you know my slides? Did you read the slides? Just kidding. NAT is a problem. Why is NAT a problem? I'm sorry? Exactly. So if I use network address translation, I will actually have a problem even before we talk about ports. If we talk about port address translation, which is the most common variation of NAT, then I have a problem that ESP doesn't have port. So how do we do network or port address translation with a protocol that doesn't have port? So we'll have that. Another problem is so many keys. Which keys am I supposed to use? I'm supposed to talk to hundreds of peers, and they all have pre-shared keys. And if you remember, the identity in the case of, so either you use aggressive mode and you have the identity of the initiator right away, but then there is a security risk, I would say, and people don't like aggressive mode, or you use main mode and you only have access to the key at the very end of the protocol when everything is already encrypted. We'll talk about that in a moment. So anyway, we have to solve these problems one way or another. Okay, so what about NAT? Well, IPsec uses protocol 50 or 51, depending if you use AH or ESP. ESP means encapsulation security payload, AH means authentication header. So if you perform one-on-one NAT, that breaks AH. It doesn't break ESP, but it breaks AH. AH is broken because the checksum of the packet is done on the header of the packet as well. If you change the source IP address, then you change the header, and the NAT device cannot recompute the HMAC, all right? If it were just a hash, the intermediate device could recompute it, but it's an HMAC. Again, crypto session, it's an HMAC. Nobody knows how to recompute this hash. Therefore, NAT breaks the AH HMAC. In the case of ESP, ESP only HMACs, only authenticates, if you wish, the encrypted data and does not cover the IP header. Therefore, you can modify the IP header without breaking ESP. There is frankly no reason at all to protect the IP header. I do not know why AH was designed the way it was. I think it had more to do with special legal use cases that some people first didn't want encryption, just authentication for speed reasons or like performance or maybe legal, I don't know. But covering the IP header, okay, anyway, AH is pretty much dead. No, hardly, who uses AH still today? One. So it's very, very rare, all right? You're really one of the very few persons I know who use AH. Do you use AH alone or AH plus ESP? AH plus ESP? AH only. I'm sorry? Exactly, so really specific, all right? And when you do this, it's mostly because performance issues and you don't want to pay the cost for encrypting when you don't need it. All you need is cover your data against corruption, all right? So it's very, very rare, but it doesn't go through NAT. Now, this being said, you could only authenticate the traffic, so hash the traffic without encryption using ESP. And this is what the majority of the customers who only do authentication, they still use ESP, but just with authentication without encryption. You can do that. So just an HMAC, no encryption. Anyway, when it comes to, so this was for NAT. ESP would work, AH wouldn't. But in the case of PAT, even ESP breaks because no port. That's what we said earlier. Okay, so NAT-T, NAT translation, or NAT transparency, actually, that's how it's called. So it's defined in another RFC, a pair of RFCs. It hasn't been a walk in the park. I think that we had 7 or 8, more than 10 in the end, revision of the RFC because they kept breaking something that we discovered in practice. We had so many cases with that and incompatible versions of NAT translation. But no, it works, of course, but it's too late. So what happens in the case of NAT-T? So first, the devices have to figure out that they are in a NAT scenario. So, you know, we start main mode exchange, classic. But when we reach the NAT device, you see that the IP address, the source IP address, which is A, is translated into B. All right, and the source port, which is 500, is translated into 1434. So that says it's which variant of NAT? It's PAT. Okay, this is technically port address translation. You have changed not only the source address, but also the port. This is typical of port address translation. Okay, the responder, oh, by the way, I forgot to say, we also send a vendor ID payload, even though it's not vendor specific, but it's still a vendor ID payload that says, I support NAT-T, so I support the RFC that we just mentioned earlier. And the responder will respond and say, I also support NAT-T. But so far, they haven't done anything special. They just have announced to each other that they support NAT-T. So now the initiator sends main mode 3. All right, now I have a question, and there is a book. What does main mode 3 contain? I'm sorry? No, not the proposals. Diffie-Hellman. Thank you. Book is yours. That's a FlexVPN book written by one of my colleagues, Graham Bartlett, and another one, Amjad Inamdar. He's the developer behind this. Thank you. So the keying material, the Diffie-Hellman keying material will be there. And there is another vendor ID payload with it, and this vendor ID contains more data. It contains a hash of the source port and the source address, and a hash, another hash, of the destination port, destination address. This goes through NAT. NAT again translate A to C and source port 500 to port 1434, but NAT is completely unaware of this hash, doesn't care. It's an application level data, not a network level, no, not layer 3, layer 4 data. So NAT doesn't care. Well, actually, NAT could care, but NAT is instructed to please not touch that because it would break the protocol. Anyway, so this hash is untouched, but the source port and the source address are modified. Therefore, the recipient, the responder, knows, can recompute the hashes the same way, and because they don't match what is in the packet, the responder knows that the source address and or port have been modified. It doesn't know what they were originally, so you preserve the anonymity of that, but you know that NAT is in play. All right, this is why we hash. We still preserve the anonymity. If you really cared about protecting your internal address space and you're going through NAT, you're not leaking any kind of information there, which is a good thing, unless you do it by yourself in the certificate or by having an identity that is an IP address and things like that. But all right, if you don't do that, if you do it well, it will be kept a secret. And the responder does exactly the same. The responder will compute the hash of the source port, destination port, and another hash, a hash of the source IP, destination IP, and a hash of the, it's Friday for me too, source IP, source port, and then a hash of destination IP, destination port. Sorry about that. So I send it there. The initiator computes the same way as the responder did earlier, sees that there is a difference, say, oh, I know I am behind NAT. All right, so initially the initiator may not have even known that he's behind NAT, but now it knows. All right, and then they can take a number of actions. There are some consequences in some cases about that, but it's not very important for now. All right, so now what do we do with that? We decide to jump to another port. We decide to switch to another type of encapsulation, which we call a UDP encapsulation. So you say, wait a minute, we already were using UDP. ISAC EMP or IKEv1 is already on UDP, so what's the big deal, right? Yeah, that's really a place I never really understood. But anyway, they wanted it completely negotiated, so now we switch communications to port 4500. The reason why wasn't really very clear. I don't see the big advantage. It actually caused more problems than solutions, but that's the way it is, and that's the way it still is today in IKEv2, by the way. So anyway, so we switch to port 4500 and we complete the negotiation, so the authentication. All right, now let me have a look. I'll go straight to the diagrams. How is this UDP payload used? Well, we also are going to put in that UDP payload, we're going to put ESP. So from now on, the IPsec packets, they're not just encapsulated in protocol 50, ESP, they're actually encapsulated into the ESP header, but this ESP header will not be put over a plain IP packet, it will be put over a UDP packet. And this UDP packet, because it has port 4500 to 4500, this UDP packet can undergo NAT or PAT without problem, and everybody's happy. All right? The IKE messages will also go over this port 4500. Now, when I receive a UDP 4500 as the responder, right, as the, on the B side here, how do I know that this packet contains an IKE message or contains an IPsec packet to be decoded? Well, if it's an IKE message, it will be prepended with 4 zeros. 0, 0, 0, 0. All right, so if you take a sniffer trace, and the content, of course, will be encrypted, but if you see 4 zeros right after the UDP header, you know it's an IKE message. If it does not contain that, it's like if it starts directly with like some fancy numbers, it is an ESP packet, and the first numbers are actually the SPI. Okay? Okay, so certificate. Yeah. I think I'll go straight to the diagram. There's no point in really talking over the text here, but the question is like, if I'm a responder, I may cater for a lot of devices. I may be a hub, or I may be a device that talks to many B2B companies, etc. Now, the initiator may also have a number of certificates. Which certificate am I supposed to use to talk to which responder? Now, you could hard code all this, but especially as a responder, it can be quite cumbersome. Besides, certificates are quite big. So if you say, well, you know, I could use any of these certificates, and you put them all brutally in it, that's a lot of, you know, that would create a really large IKE packet that would be fragmented, and we don't like fragmentation. So what we do is that the responder in main mode 4 will say, all right, it's time to authenticate. We have agreed on using certificates, so make sure you use a certificate issued by CA1, CA2, or CA3. That's what I support. If you send me anything else, I will not be able to authenticate you. So that's a hint to the initiator. So the initiator will receive that packet and see that, well, okay, I see what's called a certificate request. Let me check if my first identity, my own router certificate, ID4, is really issued by CA1 or 2 or 3. And we see that, well, no, the first identity that I have, my first certificate, is signed by CA4. It's not in the list, therefore I can't use it. What about the next one? Well, yes, my ID2 over here is signed by CA2. CA2 is in the list. Success. I could use this one. All right, let's check the last one. Could I use CA5? Oh, by the way, I don't even have an identity, but I'll check anyway. And I see that CA5 is not part of the list, and therefore I will not even try to use it. Like I said, because I don't even have an identity, I would have, you know, not considered it later. But in the first process, we exclude it like this. So now I'm left with only one certificate that I can use. Yes? What if there are two? I can pick any. I can pick any. So the question is, what if there are two valid? The initiator could pick any, and now it becomes, so by the protocol versus configuration, it's a really interesting question you ask, because yes, if there are two, by protocol I could respond with either, but by configuration I will probably specify I only want to use this one. Okay? The advantage of the method is if you're transitioning to another CA server, temporarily you could use either until the CA server is removed from that configuration, and then we fall back to the new one. But we may want to use the first one for the transition, for instance. Thank you. So there is always a difference between, and I think it's important to see that, SSL can be a secure protocol. It gives you so much leeway with the pre-master secret and all that, that actually it can be a quite insecure protocol. IKE is a secure protocol. It really doesn't let you do things that are really stupid as an implementer, right? And then you have also to realize that there is what the protocol allows you to do, and then there is what you would like to do to achieve. And that's the configuration that drives it. All right, so essentially a protocol is really only a grammar and a dictionary, but the sentences and the intent that you want to convey is dictated by the configuration. And good implementations have configuration parameters that let you express what you really want to do, not what the language could let you do. All right, I could say like lots of stupid things in English, but I have an intent, and I hope that what I'm saying is not too stupid. It conveys a message, it conveys an intent, all right? Configuration is the intent, the protocol is the language. Okay, so let's have a look at pre-shared keys, another problem with main mode. So what's the big drama? So remember, right? We create an encryption key for message 4, message 5. There is a quirk in the protocol. I don't think it's a quirk because the NSA was involved in the design of the protocol. And I don't like to bicker on them because I really admire the work they do. They're really, really strong. And I think at the time, they really wanted to do their best. They didn't try to cheat anybody like they have done recently. And I don't know if they would do it again. Again, I don't want to be contentious. I'm saying that the people who designed that, they really knew cryptography. So anyway, it turns out that if you use pre-shared keys, the final message, message 4, message 5, the keys that are derived at that moment do not just depend on Diffie-Hellman. It also depends on the pre-shared key. The problem is that the identity is hidden in that message. So now, as a responder, All right? How do I know which pre-shared key to use to generate the key that decrypt message 4 before I can decrypt message 4 and get the identity? So I have to map the key, the pre-shared key, to an IP address, which is very inconvenient if you have dynamic IP addresses on the initiator side. So that's really a chicken and egg problem, and it was very hard to solve. And this is why we ended up with a monster like IKEv2. And I really want to call it a monster because the solution for that ended up, in my view, to be more insecure than using properly aggressive mode. Anyway, that's what the industry chose to do, and there was nothing I could do about it, but we had huge internal fights about it. We acquired a company called Altiga back then that became the VPN 3000, and which code was ported to the ASA. And we had really very strong arguments about how we should do remote user authentication and how we should bypass the pre-shared key problem because, again, certificates were very complex and nobody wanted to use them. So I knew an era where people did not want to use certificates. By the way, who of you use certificates today? See, quite a few. If I had had the same question, I'm going to give you an impression. Who uses IPv6? It would have looked like that. Right. So that's the situation. So very few. Nobody wanted to touch it. Anyway, because it looked really intimidating, all right? And it took a lot of effort to break that situation. We had to develop our own CA server on iOS and then start giving classes here at Cisco Live, partner events, all of that. And little by little, CA adoption came along. But back then, you had to buy a fancy piece of software out of a company that only sold that. And it was their bread and butter. So it had all the bells and whistles and all the marketing, like we can do marketing, right? You read our marketing stuff, and you're like, is this really a technology, or is that a PowerPoint? All right? And so that was so complex. Anyway, so bottom line, pre-shared keys were difficult to use. So we use aggressive mode and aggressive mode with IKEv2, which was even worse. So a bit problematic. OK, in the face of all those problems, comes IKEv2, IKE version 2, finally. So, all right, let's try to go a little faster now. I'm going to probably jump straight to the diagrams. And we'll talk about the advantages of IKEv2 as we go along. So first off, one RFC. One, ladies and gentlemen, one RFC. OK, it's a monster to read. But it's really, really, really way much easier than IKEv1 and Isaac EMP. I can guarantee that. It's readable. You could have it by your bed. 3 pages and you're asleep. So, but it's okay. It's, in about a year, you might read it. No, it's just kidding. It's readable. No, who cares about reading RFCs? Who reads RFCs? Wow, that's very cool. So it's always good. This is what the truth is. So anyway, we start with IKEv2. There is no notion of phase 1, phase 2. I think it's much less didactical, all right? I think that from a didactical standpoint, IKE version 2 is more complex to explain, which is why I like main mode so much, because it really breaks down everything into 3 round trips, and each round trip has like a very good purpose. So anyway, in my first message, we're going to send the essay proposal. So which crypto algorithm would I like to use for my equivalent of main mode or phase 1? So essentially, I want to build a channel between initiator and responder. And here are the cryptographic algorithms that I would like to use. I would like to use a certain Diffie-Hellman value. And by the way, just like in aggressive mode, I'm not going to wait for you to agree with it. Here is the Diffie-Hellman value. Bang, in your face. The responder responds and agrees with the proposal, or select a subset of the proposal. You may propose like a bunch of crypto algorithms for encryption, like AES-256, AES-128, triple DES. And the responder says, nope, I will settle on AES-128. The responder finally chooses. Initiator proposes, responder chooses. And here is my Diffie-Hellman material. Here you are. I agree with you. It's OK. The value you sent to me is OK. You chose group 5. And group 5 it is. And then the last packet is encrypted. All right? And this last encrypted packet contains the identity. Now, that's the difference with aggressive mode. The identity was not in the first packet any longer. So your identity goes private. All right? And the proof of authentication. And this whole packet is encrypted using the Diffie-Hellman material we have just generated. And in the case of a pre-shared key, that material, that encryption key here, does not depend any longer on the pre-shared key. Does not. It opens a problem with quantum computers, but as we've discussed the other day, quantum computers are way, 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 way out. Way out. You know, for many years now, they were going to be in the next 10 years. It's a bit like nuclear fusion, all right? It's coming, it's waiting for Godot. I'm not saying it will never happen. I'm just saying that by the time it's there, and more importantly, by the time it's usable, it's really, I don't think it's a problem. No, we are working on post-quantum algorithms, and we're working on ways to circumvent that. But, you know, like I said, the smoke detectors went off. They triggered. They tripped on some smoke. We know there is possibly a risk. It's time to walk, no time to run. Walk. Let's do it properly, and let's fix the problem. So anyway, bottom line, if you're using pre-shared key, this pre-shared key does not depend, sorry, this key here does not depend on the pre-shared key, but just on the Diffie-Hellman material. So the responder is able to read the identity, and with this identity, get the key, and with the key, validate the authentication payload of the initiator. And the responder does just the same. All right, all cool? Of course, we could use certificate, and you have the certificate request replies happening over there. So it looks like IKE version 2 is a lot faster. 4 packets instead of 6. Well, you know what? It's actually 4 packets instead of 9. Because the quick mode exchange, like the first IPsec essay that we will negotiate, we will also do it with what we call a create child payload here, a child essay in IKEv2 jargon, in IKEv2 parlance. A child essay is equivalent to a phase 2 essay, or an IPsec essay if you wish. So this child essay here is created as part of the initial negotiation. We don't do a 6 packet for control plane followed by 3 packets for data plane. No, we do everything in 4 packets. Way fast, really way fast. So now let's do a comparison, right? What happens? Well, I take the protocol elements of IKE version 1, and I cram these elements that were in 6 or 9 packets, I cram them into, oops, went a little too fast, into 4 packets. Okay, so that's just, I'm not going to repeat all of that, it's just the same explanation, but what we saw before with main mode and phase 2 exchange, really the same happens with IKE version 2, just in less packets, more compact. Like I said, the protocol is easier to read, the specification is easier to read, but if you look at the protocol once it's finished, there are many concepts going on per packet, which I could break down more easily with main mode. Okay, that's it. There we are, IKE version 2. Okay, so child essay establishment. So I told you that the IPsec essay, called a child essay, is generated in main mode 1. Now, just like in IKE version 1, you want to redo a quick mode exchange every now and then. All right, you want to do it like every hour. Yes, sir?
Can you give program one slide?
Yes.
What is the bundle ports? Is it still on 500?
Yes.
The ESP is still on protocol 50?
Yes. Absolutely. Let me repeat the question for everybody else and the recording. So the question is, is this exchange still on UDP 500 for IKE and ESP using protocol 50? And the answer is yes. The answer is yes. There is also a NAT-T specification inside this single RFC. So if you need to perform NAT-T, it's defined in the RFC. So we will also perform a jump on port 4500 if we have to. Okay. Otherwise, on the wire, it's very hard to distinguish. It's only really visible in the first main mode exchange where the version of the protocol is actually specified. The protocols are not backward compatible, so there is no way that an IKEv1 implementation could accept an IKEv2 packet and hope that it works. You really have to have an IKEv1 implementation. But from a layer 3, layer 4 standpoint, they look very similar. Even most of the encoding is still the same, by the way, inside the packet. Most of the payloads are reused and are very, very similar. It's really more the grammar inside the packet that has been modified, like what you can put in each sentence being each packet. All right? So Yeah, from time to time, you want to redo an IKEv2 exchange, a phase 2 exchange, or a child essay exchange. Why? Well, maybe you have new protocols that you would like, or new source and destinations you would like to protect. If you're on the DM or a Flex VPN, that doesn't matter. But if you're on an IKE Classic with crypto maps, you may want to extend your access list. Or, but that's, in my view, the most important and the most frequent use case, because you want to refresh your keys. All right, so we have seen in crypto that the more you use a key, there is a limit to the amount of traffic you can send with a certain key before its entropy is wasted or exhausted. Therefore, you want to refresh these keys on a regular basis. With AES and with SHA-2, quite frankly, it's not so necessary. We could put the time, the repeat time, or the refresh time at a very high value. But given the type of attacks that we see these days, I'll be with you in a moment, given the type of attack we see these days, my recommendation would still be to refresh the keys on an hourly basis. All right, that's the good practice. And if you can afford, if your CPU and scale requirements afford, do perform what we call a perfect forward secrecy exchange. So renegotiate keying material, so Diffie-Hellman at this level as well, so that each key will be completely independent from the previous one, which means that an attacker who will be recording traffic and later on, maybe years later, will put an effort to get these keys and decrypt your traffic, they will have to redo that big effort for every hour of recorded traffic that you have. So essentially, you just create hell on them. Yes? Let me walk to you. Sorry, my hearing is not so good.
In view 1, you told us that the responder pushes first to the data plane
Correct.
and the initiator, thanks to the IKEv3 packet,
Yes.
pushes the data plane.
Yes.
What about V2?
This is a fantastic question. Thank you. So let me repeat that for everybody. So I said that we had 3 packets in quick mode for IKE version 1. And here, when we receive this first phase 2 packet, this create child essay, the first create child essay packet, we'll start pushing the keys to the data plane. And then we'll tell the other side, fine, you can do that too. And this guy will start pushing. But before the data plane is ready here, that device here could start pushing packets encrypted. And this device here may not be able to decrypt them. And you would see a message that is, how is this message called? On the console, you get a message when it happens. It's called invalid SPI. I received an IPsec packet, and I don't have a corresponding security association. Actually, it's there. It's somewhere in the memory, but it's not yet ready in the data plane. And the data plane says, I can't do anything with it. And we did have the problem. So we had to install a timer here, a sufficient timer, so that it doesn't happen. And then that was like a really bad workaround, because it means that we couldn't start encrypting before a few seconds. So that was really annoying. So what did we do is, as we generate the SPIs over here, so this guy chooses the SPIs to be used, it starts preparing the data plane. Then we send the child essay exchange. So we prepare the data plane by saying, OK, we are going to use these SPIs, but I don't have the keys yet. Just be ready, all right? And then we send the SPI and the keying material and the proposal there. This responder says, OK, fine. The responder pushes the whole shebang to the data plane, starts using it, responds to us, all right? And in the meantime, may start sending encrypted packet, but our data plane here is ready to say, yeah, I know, I'm going to drop a few. I don't know what to do with it, but I'm not going to cry over it because I know the rest is coming. And once we receive the control plane packet here, we push the rest of the security association. It's a very expensive operation because we have to do 2 control plane programming. And that's a bit of an issue in reality, because control plane is very expensive. We have to reprogram TCAMs, we have to reprogram the crypto engine, we have to reprogram a whole bunch of things. It costs, it's a few 100,000 lines of code that we have to go through, right, and execute. Clearly, the protocol here, we really complained over that, but nobody would understand or agree, because most vendors who were behind this only had software implementation, not tight hardware implementations. And so the hardware vendors, they just had to suck it. That's the way it is. But this protocol was really meant with a strong use case, remote access. So software implementation, remote access. So that, yeah, I think for me that was kind of a failure of the IETF process to cater or to avoid catering for hardware vendors, but that's the way it was. We overcame it, you know, and it works. So, you know, we stopped fussing about it. But it's a very good question you asked. It really caused a lot of problems to us. And so when we saw the protocol coming, this was exactly the reaction that all of us had. Why? Because we knew why, you know, the explanation I gave you about how we push quick mode, all right? It wasn't like that from day one. We actually iterated until we figured out the right way to install the keys without having those race conditions happening. And so it was still fresh in our memory. I mean, most of us had history, and when we saw the protocol, there was exactly, why? Why did you do like this? It's breaking everything. And so, yeah, thank you. It's really history. All right, so version 2 is super fast. 2 round trips. Da-da-da-da. Isn't it wonderful? But it's not fast in reality. Well, it can be fast, but it can get really slow. So because we send the Diffie-Hellman material in the first packet, how am I doing with time? I'm good. Because we can send Diffie-Hellman material in the first packet, just like in aggressive mode, we could bombard the responder with Diffie-Hellman computations. So drowning the responder CPU under a DDoS attack, for instance. So what do? We generate what is called a stateless cookie. And it's a stateless cookie similar to the SYN cookies. Who's familiar with SYN cookies in TCP? Okay, only a few, all right. So that's something that appeared on Linux. I think it's a genius move that they made to protect against SYN flooding. You know, SYN attack flooding. SYN flooding consists in sending to a victim, a target, like a lot of SYN packets, TCP SYN, and you will never bother about sending, like, of course, the target will respond with SYNAC and create an entry in the TCP control block, the TCB, you know, and send back like, okay, SYNAC, and SYNAC, oh, SYNAC, I'm waiting for your ACK, but we never care. We're the attacker, all right? We just bombarded this station with a lot of TCP SYNs. The TCP database, the TCP control blocks consume all the memory, and the device becomes catatonic. It's a denial of service attack. So we could do the same with IKE, and we implemented a similar mechanism. When I say we, it's now in the RFC. Notice that IKE version 1 also had a cookie protection system, but this I never understood why. It was completely broken. It was like a flaw in the protocol. It was useless. This one actually is relatively useful. How does it work? Well, the initiator sends a message 1, SA init it's called, with the Diffie-Hellman value and the whole proposal. And this device here says, am I under attack? Well, maybe I am. How does it know? It doesn't know. It may be a very legitimate packet. So that's the problem with denial of service attacks. It's very difficult to make the difference between a legitimate and an illegitimate packet. So how do we know? I don't know. So instead of creating state and allocating memory and all of that, I'm actually going to have one random number in my memory. And out of that random number, and by the way, this random number, I'm going to change it every minute. But it's not very expensive. It's one, you know, roll the dice, you know, every minute. It's just that, a few bytes. So with this random number, I'm going to generate a cookie. And this random number, by the way, I'm not telling it to anybody. But I'm going to generate a cookie. And what's a cookie? Well, I'm going to take the whole packet here. Actually, I'm going to take all the individual payloads in the packet. And I'm going to hash or create an HMAC, if you wish, of that random data with the random number I have in memory. And I'm going to send back a message to the initiator without creating any state. I'm just responding, and I'm going to add that cookie, that value, inside the packet. And I'm not even going to bother, me, the responder, I am not even going to bother remembering that cookie. When the packet comes back from the initiator, so let's say it's a legitimate initiator, when the packet comes back from the initiator, it has to contain the same data as before, plus the cookie. And what do I do with that cookie? I will recompute, well, I will take the vendor, all the payloads over here, minus the cookie, and recompute the HMAC and compare with the cookie that's in the packet. And because the HMAC depends on the random number that I keep as a secret, nobody else can have generated this. So I have a proof that I'm talking to not a zombie, but something that is live. Is it a perfect protection? No, it's not. but it really protects well again, like basic attacks, basic denial of service attacks. We don't see so many denial of service attacks today. Usually they are more vicious. You try to inject code and things like that. It's a simple mechanism. It's a simple protection, and it does what it's supposed to do. But it introduces possibly and randomly an additional round trip time. So how long does it take to negotiate an IKEv2 exchange? Well, it depends. It could be 2 or 3 round trips. If you add to this that it may not be the right Diffie-Hellman material, add another couple of round trips, right? Or another round trip. So that's 2 more. Okay, no, we are at 4 round trips. Okay, so pros and cons. In practice, though, it turns out to be more efficient in terms of round trips. IKEv2 tends to be more efficient, but this can happen, just beware. All right, where are we? I'm just checking on the time. I don't want to run over. Perfect. Okay, so yeah, like I said, which Diffie-Hellman group we will accept, whether or not we'll have to try again and have a cookie protection or something like that. Yeah, this actually will play a role. So I want to show you what happens if we send the wrong Diffie-Hellman material. In this case, my initiator proposes, let's say, Diffie-Hellman group 2. This responder here only wants Diffie-Hellman group 5, or 14, sorry. And it says, well, no, I don't like what you're proposing to me. I ignore your Diffie-Hellman material. I am not even going to compute anything with it. Please send me group 14. And so in the response, we're going to have a message saying invalid KE payload, invalid key material payload, so invalid Diffie-Hellman proposal. Please send me group 14 instead. It will be part of the vendor ID payload here. All right? All good? And of course, the initiator will resend the packet. We'll have to recompute a new Diffie-Hellman and resend. Now, is it a problem in practice? Not really. So we saw a lot of configurations with version 1 where people configured pretty much every algorithm that they could, every Diffie-Hellman in the order of preference, every encryption algorithm in the order of preference, and so on and so on. All of that on duplicated on the head end. And in any case, the head end will pick only one, the first one in his list or her list here. All right? So is there a sense in configuring all of this? Probably not. Now, if you're going to talk to multiple enterprises, like in a B2B environment or something like that, you may want to have this router talk to one head end that will only support, let's say, Suite B or Advanced Suite B with a SHA-2 and AES-256, whereas it may also connect to another device that only support AES-128 and SHA-1, for instance, which is still legitimate. Fine, fair enough, you can do that. But the Diffie-Hellman values themselves, they're usually the same. Okay, so usually we recommend them high. So it can happen that in some environments we end up with multiple Diffie-Hellman valid proposals and only one will be accepted by the remote peer. Yes, that's one more round trip and more computation to be done here because we have to recompute a new exponentiation. So it's a bit of a problem. Then again, the protocol was really designed initially for the remote access use case, which is the most prevalent. I think still it's kind of a weakness in my view, but anyway, that's the way it is. So IKEv2 is a protocol I would recommend hands down today. Don't go for version 1. Don't take my comments as like, oh, I don't like V2 and really you should stay on version 1. That's not what I'm saying. I'm just saying a lot of, IKEv2 has been gratified with all the benefits of the world. I just wanted to show you that, yeah, not everything is perfect if you analyze the protocol. Okay, so one more place where we can have more exchanges, and I think here it's not a drawback, it's an extension that was really badly missing out of IKE version 1. We fixed it with Xauth and mode configuration, mode config, but it was really poorly done. I think that this is not a disadvantage or something that makes the protocol longer compared to IKE v1. It's something we used to do in v1. I didn't show you how it worked because it was really badly broken. I'm going to show you how to do that in IKE version 2 only. So, and it's called EAP authentication. So that replaces the exchange we used to call Xauth in EasyVPN. Okay, so yeah, here is how it works. At first, the PC here has a user. It's the initiator, but there is a user behind. And we would like to know, it's not enough to have the PC from your company. It's actually important that the user at the PC is actually also from your company, because the laptop could have been stolen, right? So this exchange here will start as normal, and the PC will authenticate. When we reach this point, the authentication payload will be empty. It will say, I don't want to authenticate myself. All right? You see there is an identity saying I'm the PC of your company, but there is no authentication payload here. There is directly you can see create child essay. It's like, wait a minute. Just like that? Well, not just like that. It means we want to start EAP. Now, EAP, the client doesn't really get to choose what it does. The AAA server does. Actually, the server may not even choose itself. So what we're going to do is first, we're going to authenticate the server. So you see here, what happens is, even though the client has not authenticated itself, we authenticate the server. Why? Because the user is about to type its passphrase, and some EAP methods are not so secure. I mean, on their own, they're not secure. It's only secure because they are encapsulated in a secure protocol. So you don't want to send like a password in the clear over an EAP payload that would be decrypted by a rogue server, a rogue hub, or a rogue remote access server. All right, you want to prevent against that. So the server will authenticate itself. Essentially, we'll go back to the same situation as SSL. Let's first authenticate the server. Whereas in IKE, we usually, oh, you want to talk to me? Tell me first who you are, right? But here we go back to, okay, well, we have to authenticate the server. No, the PC can trust the server, and we can have use, for instance, certificates. Now, it's time to start the EAP exchange. So over IKE, we're going to piggyback additional payloads that allow an EAP authentication to take place. And the authentication will typically take place between the client and the Radius server. So at the Radius server. Here, all right, the hub, the IPsec IKE server, the remote access server, however you want to call it, will just decapsulate that data and put it onto the Radius packet. Maybe do some translation like for encoding purposes, but there is really not a lot to do. And it will send that over Radius. And it's the Radius server that will tell, yes, you're authorized, or not, no, you're not authorized. And it may be in a single exchange like, hi, I'm Fred, and my password is Cisco123. And I would send that in plain text over IKE. All right? And that would be sent to the Radius server, and the Radius server will say, yeah, authorized. Access, accept. Or, and that's a lot more secure, I would use EAP-MD5. Still not good because it's MD5, but better than plain text. Or I could use PEEP or LEAP or whatever type of authentication I want. And all of a sudden, there can be a number of round trips between the Radius server and the client, and there can be quite many of these. It could be that we have to create a TLS session between the client and the server over the IKE channel. And when this is done, when the AAA server will have fully authenticated the user, given whatever method, by the way, the AAA server may have to talk to your LDAP directory or to your Active Directory, et cetera, et cetera. So, there can be a cascade of servers down there. When we're done, then finally we tell the server here, access, accept. And maybe, in the best cases, in the best EAP cases, this access accept will also contain keying material. That keying material, generated by the AAA server, will be used to authenticate so that the hub, the server here, can finally trust the client. So you could say, well, wait a minute. This guy, this AAA server here says access accept, all right? And why wouldn't I trust the client? Well, we want to go one step further and make sure that the user here really had all the data necessary to compute the key. So from here onward, using the keying material that was negotiated between the PC and the user and the AAA server, we're going to go through an authentication phase, a last authentication phase, and use the keying material as if it were a pre-shared key. So essentially, at the end of the EAP authentication, keying material will be generated between the client and the AAA server, and that keying material will be used to perform an IKEv2 pre-shared key authentication. And that concludes the protocol. So that's quite a few packets. It's a tough one, right? You really have to see it in action to start appreciating how complex it can, how it works. And in the worst cases, or in the most complex cases, I mean, EAP would probably be the subject of a complete session. We used to present it in FlexVPN sessions, and it blew everybody's mind. I mean, essentially, the room temperature went up by a degree. But OK, it's there. I think EAP is really something that deserves a session here at Live. But I don't know if there would be so much demand for it. Don't hesitate to ask. OK, anyway. And finally, we create the child essays, and everybody's happy. OK, good. So bottom line, is IKEv2 faster? Yes, it's faster in general, but there can be surprises, and don't count on the fact that it's only 4 packets. So essentially, what I want to draw, I want here to draw your attention on a lot of literature says IKEv2 is fantastic because it's so much faster. It's only 4 packets, and I'm like, wait. In practice, it's usually a lot more, especially for remote access. So don't count on it if you have to do tight measurements or if you have tight requirements in terms of session establishment time. So what's the whole thing with IKEv2? Well, we can say it's more secure. We can say that it supports Suite B. Well, actually, we can have Suite B in IKEv1 now. I think that the biggest interest is it's as efficient as aggressive mode. It doesn't have the drawback of main mode of IKEv1, so it really combines the best of main mode and aggressive mode. That's what I like. It allows you to use pre-shared keys even on a remote, on a AAA server. I think that's a really big plus in terms of security. Not that the previous one was insecure, but in IKEv1, because you couldn't map the pre-shared key to an identity and you had to map to an IP address, people tended to use what we call a wildcard pre-shared key, so the same pre-shared key for everybody. So the difficulty of management made the protocol insecure. In this case, we removed the barrier to the management. We can associate names like email addresses, FQDNs, to a pre-shared key, and we can do that resolution even if the IP address is dynamic. Therefore, it is more secure because true security is more manageable. And I think that's a critical element of security. If it's not manageable, people don't do it. And if we don't do it, it's not secure. It's like medicine, right? They only work if you take them. So, all right? Yes? So the question is IKEv1 greedier in terms of resources, consumption, and everything? Not by definition. It turned out to be because it was the first implementation we had, and we evolved with the protocol. In the beginning, we didn't know where we were going, and I remember when I started with this, the first prototypes were out. It was pre-RFC. There were some really crazy ideas about what IKE and IPsec had to look like, and we developed a lot of code that turned out to be useless later, but there is never any time to clean up. So with IKEv2, and that's actually going to be the last part of my presentation, we were given an opportunity to get a clean slate and re-implement virtually from scratch. And that's, I think, one of the other advantages with IKEv2 is that a lot of complexity that we introduced in the protocol in the early days, we tried, we failed, we tried something else, we modified. We tended to have like very organic code, not so optimized. When IKEv2 came about, we say, okay, we can't really convert the code. Let's rewrite, let's make it clean. That's what happened. So it turns out that in practice, IKEv2 tends to be a little tighter. Yep. Is there some? Good question. Is there a mode config to push an IP address, DNS, and so on? Yes, it is embedded inside the IKEv2 protocol, and we use it extensively in Flex as well. So that's how we actually exchange a large number of parameters like that. If you attend a Flex session, we use that extensively, yes. We even exchange routes over it. So we can get rid of routing protocol. So if you're on DMVPN, for instance, we can in FlexVPN use the mode config attribute to exchange the prefixes, so we don't have a routing protocol any longer, which means that we can scale better. And so to your question, it consumes less memory. So IKEv2 with mode config ends up consuming less memory than IKEv1. We scale better, 10,000 branches, all right? And because we don't need the routing protocol either, it scales even better. So yeah, but that's I would say a practical effect. It's not because of the protocol, so to speak. It's because our implementation is better. We have more experience. OK, so what does that all look like? There's a lot of options in IKEv2. And here I'm going to show you something that's more iOS specific, but yeah, I guess it's always useful to see what it looks like in practice. You can end up with an IPsec, with an IKEv2 profile that has authentication remote pre-shared and authentication remote EAP. It means that I want the remote peer to do either EAP or pre-shared. All right, I'm the server. I don't care if my remote devices will authenticate with EAP or pre-shared keys. Do I see that a lot in practice? No, but I can. All I have to do is specify multiple remote methods. How am I going to authenticate myself? We use the keyword local, authentication local RSA signature. So essentially, I'm going to use, me, the responder, I'm going to use an RSA certificate to authenticate myself. It says something really interesting about the protocol. It means that now you can have asymmetric authentication methods. You could have a device on one end using pre-shared key, the other device on the other end using certificates, for instance. That's allowed in IKE version 2. In IKE version 1, we had an implementation that could do that, and we could do what we call hybrid authentication, but it was not even an RFC or even a draft. Okay, so that's the kind of thing we can do. Attribute exchange, back to your question, do we have a mode config? Yes, this is the mode config I was talking about. All right, and in the case of Flex VPN, we actually run into the situation. So with DMVPN, you have to run a routing protocol. You have to negotiate IKE and etc. So there is an overhead in running a DMVPN with a routing protocol. It's about 175 megabytes per month per device. Now, if you're a utility, for instance, or like ATMs or like an IoT device or something like that, and you pay per packet, and that happens quite frequently, and you have millions of devices out there, this starts being really, really expensive. So with mode config, we can push an IP address, etc., plus a bunch of routes, and we can reduce the total number of packets to virtually nothing, just the rekeys. And this is the solution that we see the most in the IoT deployments. We have really massive deployment, 250,000 nodes, 1 million nodes, and that they are virtually silent, and they do all they need to do with just IKE. Okay, that's one use case. It's not the most frequent use case, especially here at Live, but it's a very important use case for us. I mean, there are few networks like this, but the networks that exist, they're really massive. Okay, fragmentation. IKEv2 supports a fragmentation reassembly of the IKE packet. So if you're going to send big certificates, or at least a certificate, a certificate alone could exceed what you can send in a single IP packet, MTU 1500. Well, IP packets can go up to 64 kilobytes, but nobody has 64 kilobytes MTUs across the path. Most of the time, it's 1,500 bytes or less. You may have some giants allowed at places, but it's usually not end-to-end. Most of the time, end-to-end, it's 1,500 or below. And in some countries, it's really, really small. It's around 1,000. So this will create fragmentation of the IP packet. So you create a big UDP packet, IKE message, and it gets fragmented at IP level. And IP fragmentation is really bad because if you lose one segment or one fragment, you have to retransmit the whole thing. And you have to have a protocol that says, I didn't receive anything. And you retransmit the whole packet, it gets refragmented. And what really happens is that this creates microburst because you have one packet, and all of a sudden a router creates 3, and these 3 packets, they are burst out like very fast because data plane doesn't have the time to wait. So it bursts all the 3 packets out. And these 3 packets, they may exceed the committed rate somewhere. And so one of the fragments will be dropped. And you have to retransmit the whole thing and essentially have a continuous effect of every time you fragment, you create a microburst, and each microburst causes a fragment to be lost, and you never manage the negotiation. So that's an extreme example, but it happened, and it was very annoying. So IKEv2 supports fragmentation. So when IKEv2 detects the MTU or is given the path MTU, it can decide on its own to instead generate a big packet that we fragment next. We first fragment the UDP payload, where IKE first fragments the UDP payload and sends the fragments of the UDP payload over dedicated IP packets, which can be acknowledged at the IKE level separately, pretty much like TCP does with segments, right? And because we can acknowledge the various segments separately, we're good. We just need to retransmit whatever got lost, which means that we finally succeed the negotiation. So that's a good feature to have. Where do we use IPsec and where do we use IKEv2? Well, ASA and FTD have an IKEv2 implementation. AnyConnect uses SSL or IKE version 2. Now, most people are on SSL. Who uses SSL AnyConnect? Yep, quite a few of you. Who's on IPsec? Oh, I'm actually impressed. So many times over, we are being told by marketing that nobody uses IPsec and IKE. In the TAC, we don't quite see that. But we see more problems with SSL than with IKE. So our view is kind of skewed. And that's probably due to a protocol implementation level. So that's something that I would like to mind when I go back home. But anyway, so we do support IKEv2 and IPsec in remote access. I would like to highlight that, again, I have nothing against whatever people do. SSL is good to me if you like it, no problem. I would recommend that you do performance test in two situations. What happens if you transfer a TCP file over plain TLS, not DTLS? All right, who uses DTLS? Some of you, some not sure? Who's not sure? Okay, check it out. So DTLS is packet-based. IPsec, ESP is packet-based. TLS is TCP-based, so it's a TCP system. So if you put a TCP packet, if you encapsulate a TCP packet inside the TCP packet, if something gets dropped in the middle, you will retransmit probably 2 times. One at the protocol level application layer, and another time at the VPN layer. All right, so it can be really annoying. And same thing with voice data, RTP streams. RTP streams are made like this. Either they make it on time and they're good, or they don't make it on time and it's just as good to drop them. So, but if you're going to retransmit, you may have actually longer outages with RTP frames. So check out if you're using TLS or DTLS, but TLS can actually have these side effects. Now, a lot of people claim that IPsec and IKE doesn't pass well through firewalls, and I'm sure I have seen experiences like that, but most of the time, I don't see the problem personally, and I travel quite a bit. Anyway, that's a choice. And we only support, in this case, on ASA and FTD, we only support remote access cases for which we really excel. I think the feature is very, very rich. However, from a site-to-site standpoint, we only support cryptomap-based VPN. And if you have attended the session with Piotr Kupisiewicz at the beginning of the week, that was talking about Flex VPN. We are all from the TAC, and we are all saying the same thing. I only need 4 engineers to support worldwide IPsec iOS, and I need 10 engineers to support in a given time zone, right? And I need 10 to 14 engineers to support ASA, right? Because crypto maps create a lot of issues. So that's the difference. So we see much less configuration issues using a Flex VPN or a DM VPN with tunnel protection than we see with crypto maps. So it's not, again, bickering or because I like the feature more than another. All of that was created with a purpose, and it's the TAC. No, again, I'm not encouraging you to drop your hardware and buy a new one. I'm not a salesperson. Like I always say, I prefer going for a beer with you than having a case with you. So, a beer or tea, I mean, whatever. I like both. So, for FlexVPN, I just mentioned, FlexVPN is a very complete solution. It supports both remote access and site-to-site. You can run routing protocols over it, or you can use IKE as a routing protocol. The whole configuration is rather simple. Its scale is extremely large, like extremely wide. So we support up to 10,000 connections per device, and they're really 10,000 connections per device, like not marketing numbers. I mean, they're also our marketing numbers, but they're real. We try them, so for sure it works, and it works like it should. So. There are many redundancy options supported, so it's probably the most complete site-to-site implementation we've had. In site-to-site, it really shines. In remote access, it's still a little rough at the edges. It's getting there. It's not as good as ASA, but it does provide quite a large set of features. And again, if you look at the FlexVPN session from Monday, you'll see what to do. Most people prefer to stay with ASA for remote access. Okay, so maybe another example on Flex, and again, these are Jay's slides, so I'm going to do honor to his presentation. The default values, all right, there are many, many options in IKE and IPsec. So who thinks BGP is complex? Nobody? Wow. I often hear BGP is complex because it can do so many things. And I can assess it is true. My take is that it's only complex if you try to do everything. It's usually not complex if you have a use case and you understand your use case. Same thing with IKE and IPsec. Do you have to know all the tiny options everywhere? No, there are many, there are dozens, hundreds of options. The protocols, the algorithm, the math, all of that is complex. But if you have a use case, it really boils down to this, and this is a complete configuration. All right, there are many parameters that are set by default. We do evolve the defaults. The crypto algorithms are chosen for you if you don't want to override them, and we maintain them to a high security level. We just bumped the Diffie-Hellman group from group 5 to group 19 for security and performance reasons. So it's updated, and when you will upgrade your iOS, you will inherit this new Diffie-Hellman group, and we made sure that it's backward compatible, so if you upgrade on one side and not the other side, it will fall back to the old Diffie-Hellman group, and when you've upgraded both sides, automatically you get the new value. So we do pay attention to maintain that. So the defaults matter a lot. Now, IKE IPsec is only an encapsulation and a security protocol. On top of that, we receive a lot of queries about, well, remote access, side-to-side, they are use cases, but then we want to cater for a backup. What happens if my server fails? How do I fall back to the next level? All right, and that is when it goes back to, there is a protocol with a vocabulary and a grammar. All right, what can we express with it? We can express your requirement through configuration, but we can also express use cases by intelligently using the protocol to do things. So what kind of things can we do? Well, the redundancy model. So for instance, you can have in IPsec, you can have two tunnels active at once. If you just take the RFC alone says, well, you generate a security association that says, encrypt my traffic going from here to there. There is nothing in the RFC that tells you, oh, and by the way, if the remote peer fails, switch over to that device, or load balance across two devices. In fact, with a crypto map, you cannot even express that type of thing. So by intelligently using the protocol, by using GRE IPsec, by having dual tunnels active at the same time, we're able to achieve always on. It is still IPsec. It is still, strictly speaking, the standard that we just discovered today. But by using it like in a little smart way, we can create active tunnels. Same thing, we can create redundancy scenarios where we connect to a preferred hub, and if it fails, we detect it and we fail over to the backup hub. Right? So again, this is not in the RFC. This is something that we have decided to do on top of the protocol, with the protocol, without even breaking compatibility or without breaking the RFC, just by paying attention to details. Last thing, what we call the HSRP load balancer. It's not the last thing, actually, one more. The HSRP load balancer, we could actually create a cluster of IKEv2 servers. So essentially, as you grow, right, initially you have two devices, one primary, one backup, and they can be active at the same time until one fails. So this is really cool, right? You have an active and a standby. You need the active, but instead of the standby doing nothing, you could actually start loading it, and you have just more throughput, more performances, lower CPU. I mean, you just sleep better. And if one fails, we just fail over the connection to the standby only, and it keeps working. But now when you need more than one device to handle all the connections, you add one more, and then one more to the cluster. And you keep adding without even needing a load balancer. So this, again, we can do, not by breaking the protocol, but by using the protocol. We have implemented what we call IKEv2 redirect. Okay? And finally, what we call the source pivot, the tunnel source pivot. If you're dual ISP based and you would like to use one ISP while it's active, but the other one is like less preferred, more expensive, whatever the reasons, maybe it could be like your main line, like an optical line, and you have a backup over 4G, for instance, pay for, by the minute or by the packet or whatever else, or subscription limited. But when the primary link breaks, we can switch over to the backup ISP, and we can do that without increasing the total number of tunnels at the head end. So essentially, from a head end standpoint, this client will come with one connection either via ISP1 or via ISP2, never both at the same time. So essentially, the scaling of the head end stays normal. Yes? Based on what can you use as a trigger? What can we use as trigger to switch over? Anything you'd like that we can detect, that is interface goes down, or a root goes down, or IP SLAs, or you can actually even script in Python on the device itself, and based on the result of the script, whatever combination you want to have. We have customers doing RSS, so signal strength and stuff like that, and they decide based on these parameters to do a computation with a Python script, and the Python script pilots the switchover. We have an API for that. So again, it's not in the RFC, but nothing prevents us from doing it. So the RFC is, I mean, there is always a naive way to analyze the RFC, and then there is the creative way to use it. We support the naive because we have to comply to standard, but we also have creative elements. Something that we mentioned earlier, we took the opportunity to rewrite, so we have now a better CLI, we have better feature sets. We also have better debugs. The IKEv2 debugs have been entirely rewritten, again, with the help of our tech engineers. All right, we have worked together. We have tried the debugs on them on many occasions, and we have honed and cleaned up the debugs best we could. Is it perfect? They're still debugs. They're still relatively arcane. They still require a good degree of knowledge, but the quality of the debugs allow you to understand. You read the RFC, you activate the debugs, and you should be able to follow the RFC with the debugs. I learned IKE because the first developers had good debugs. And then they made poor debugs. And we told them, no, the debugs were good. Please make them good again. And we did that in IKE version 2. Okay, we think that debug should be there to teach you what the system is doing. If you have to know how the system is supposed to work before you can use the debugs, they're very hard. So we rewrote the debugs too. Again, that's iOS, not ASA. Yeah, there are 2 sessions. We're really reaching the end of the presentation, right? So there are a couple of sessions I would recommend. This one was given last year. It's an introduction that compares all types of VPNs that use mostly IPsec, IKE, TLS, and all the variations, including GetVPN and DMVPN and Flex and remote access and whatnot. That was given last year, not this year. This year we had BRKSEC 3054 given by Piotr Kopiziewicz. It was initially my presentation, but he took it over. He did a very good job with it, very nice prezo. And then there was the crypto, I forgot to specify it, but there is a crypto presentation, BRKSEC 3005. If you're interested in the cryptography, how does AES work, what is AES GCM, what's Diffie-Hellman, what's elliptic curve, versus RSA, all of that. We don't have the time to cover this here, obviously. From a literature standpoint or references, there is an excellent book by Graham Bartlett and Amjad Inamdar. That's the book I gave away earlier. It's very exhaustive. It covers a lot of designs. Again, it focuses on FlexVPN. And why FlexVPN? Simply because from a remote access and site-to-site standpoint, it's pretty much the only solution that does it all without fuss. It works. I mean, we think it works well. Okay, so in summary, IKEv1 works well. There really was not many problems left with it. It's always the same, right? When you finally fix all the problems, we scrap the protocol and we start over with a new one, and we create new problems. But the truth is that IKEv2 really gave us more security, better extensibility, especially with mode config and EAP authentication, and most importantly, gave us an inflection point to rewrite our CLI or debugs or optimization so that we have a better world to play with. Yeah, so I guess that was it. That concludes the presentation. I didn't have a session manager today because they all flew away. And this being said, I thank you very much. Happy end of Cisco Live and safe travels.